Alright, in today's lesson we're going to start learning about thermochemistry and thermodynamics. And our objective for today is just to differentiate system and surroundings as well as exothermic versus endothermic processes. So I'm going to show a demonstration of each type of reaction, and we'll talk about the energy flow within that process and what a diagram of that might look like. So the first reaction I'm doing is a reaction between barium hydroxide and ammonium thiocyanate. I've already mixed it, okay? But this is going to be an endothermic reaction which absorbs heat from the surroundings. It's going to get really cold, and if you touch it, it will feel really cold. At first, this system is not going to have much energy, but what it's going to do is pull energy from its surroundings to increase its energy. But one thing I want to illustrate here is that the total energy of the system and the surroundings combined doesn't change. The total energy in the universe does not change. It just gets transferred from one form to another. So in an endothermic reaction, the system increases in energy while the surroundings decrease in energy. And to show proof of that, as I pick this up, the solution got so cold once I reacted the two substances that I had a little bit of water underneath it, and it froze the water underneath it because it pulled energy away from the water, causing it to freeze. And since this is a wood board, pretty porous, the ice was able to basically grip in there and hold these together. If we look at an energy diagram for a process like this, you're going to see that the reactants start with lower energy and the products have higher energy. You'll notice this hump that exists in this diagram for a chemical reaction. Because what has to happen for a chemical reaction like this is the two reactants have to separate to their component ions and break bonds. In this case, they're ionic bonds that they're breaking, but the first part of this graph represents bonds breaking, and that requires a lot of energy to happen. The second part represents new bonds forming. So there's new compound formed in there. You have barium thiocyanate that form. When that forms, it releases only a little bit of energy. So the total system gains energy as it becomes its products. If I were to do an exothermic reaction, something simple just as lighting a match, you can see that energy is being released by the system's surroundings. It's doing two things. One, it's making the molecules around it move faster, giving them kinetic energy, and it's also exciting electrons within those molecules, causing them to give off light. And you can see that the potential energy of this has been reduced and transferred into kinetic energy in the surrounding molecules. So at first, our system had a lot of stored energy, a lot of potential energy, and the surroundings had a certain amount. After the reaction occurred, the surroundings increased the amount of energy that it had, and the system dropped. But again, the total energy in the process is conserved. If we were to look at an energy diagram for this type of exothermic process, the reactants again have more energy than the products, but it still took some energy to be put in order to start the reaction, or activation energy. That got the bonds to break so that the new bonds can form. In this process, the amount of energy associated with the bonds breaking was far less than the energy associated with the new bonds forming. So overall, it was an exothermic process. The total energy change of the reaction be given as the products minus the reactants. And this right here, the E sub A you see here is the activation energy, or the energy required to initiate the reaction. All set.